Okay, I'm on. Thank you, Mitch. It's great to be there virtually. As you can see, I'm going to use the setup that I used for when I taught virtually, which is on a whiteboard in my home office. I think it's pretty readable, but please let me know if something is a little obscure. I can always try to write bigger or write something again. So I'm going to be telling you about braid groups and the Burau representation of braid groups, which is a very familiar topic to many of you. But when I was asked to have a bit of an emphasis on tutorials, and maybe I'll be a bit more tutorial than some of the other speakers were. So forgive me if you know all this, but I'm pretty sure not everybody knows everything I'm going to say. And the goal here will be to say how I personally use the Burau representation in some analysis of dynamical systems. So, of course, we know very well the braid group, denoted Bn, and here I have in mind the braid group on the punctured disk or on the punctured plane, whichever you prefer. And so n here is the number of strands of my braid, or the number of punctures, if you will. So I picture something like a disk, and there's n punctures. And the braid group, of course, was invented by Artin and is used in many areas. And its best way to represent it is in terms of generators, which we call sigma I. Let me use k because I use k in my notes. Sigma k. There are n minus 1 of them. Trouble writing? Okay. There are n minus 1 generators, and each generator corresponds to, my convention will be that each generator is the clockwise interchange of neighboring punctures. So this is sigma k will exchange the k and k plus 1 puncture. Of course, the inverse operation just reverses the puncture counterclockwise or anti-clockwise. Okay. So that's the first important defining property, and you generate all possible braids by composing these operations together, therefore making the braid group. So the braid group obeys what's called relations, or the generators obey what's called relations, and I'm just going to quickly present them here. The quick way to express them is 1, 2, 1 is 2, 1, 2. That is the most important relation, or it's a set of relations. For any k, there'll be k, k plus 1, k, and then k plus 1, k, k plus 1. Of course, the best way to prove this is to draw a quick picture, and then it becomes obvious why this is true, according to a braid isotopy, right? If you allow yourself to deform the braid. There's a question in the, there's a raised hand in the chat by Chin. Yeah.
Luc,
yes.
Could you please zoom out a little bit? I cannot read the left part of your whiteboard.
Oh, that's interesting. So in the camera view that I have here, I see it. Can you tell me what's the line?
It's split on the B braid group.
I'm sorry?
The braid group. I can only see a D.
Okay.
Braid group.
The edge is going through the B of braid group.
So here.
Yeah.
Okay.
Yeah.
Okay. Thank you, because on my little view I can see everything, so it's just a different viewpoint that you guys have. Okay, so that's good to know. I will renormalize. Is this visible?
Yes. Your capital B is not visible.
The B is still off the screen.
That's not true. Yeah.
Is that true for everybody, or is it just Chin? Because sometimes these things are camera view dependent. So I'm going to say something like this. Okay.
Can you just zoom out a little bit?
I don't have zoom control on this thing.
Okay.
Yeah, there's I don't really have a zoom setting. I think it's as zoomed out as much as it'll go, basically.
All right, that's okay. That's okay. No worries.
Okay, so I'll keep within the bars. Right, so as I said, there's a sigma k, 1 less than k less than minus 1. This is the well-known braid relations. Actually, why don't I draw them quickly, because it's so easy. Right, it's basically saying that this diagram is the same as this diagram, right? So again, you've all seen this, and you can kind of clearly see that there's one strand here that goes. Oops, did I draw it wrong? I think I managed to draw it wrong. Yeah, I'm missing one more piece, right? I tried to do it quickly, and I failed. There you go. Yeah. So 1, 2, 1 is 2, 1, 2. And here I'm using the standard, my crossing definition is that this is a positive crossing. But again, it's just a convention. And I'm reading them up, but again, also just a convention. But you can kind of see now that the middle string just connects the middle to the middle while remaining between the other two strings. So that's one relation, one set of relation, and the other type is the commutation relation. Right, that say 1, 3 commutes with 3, 1. So anytime two strings have a distance more than 1 apart, so if two crossings don't share a string, then they commute. You can slide them up and down the braid. Okay. So again, I'm sure very familiar to all of you. Right. So there's an interesting viewpoint of the braid group as the motion of particles on the plane. So if I have, for instance, some data, and often I work with data from floats in the ocean. So you might have North America here and South America, and maybe you have Europe and Africa, and then you have some floats moving around the ocean, a series of floats, and you have data for the position of these floats. You can lift the motion of the floats to a space-time diagram, and make what people often call a spaghetti plot for obvious reasons. Okay, so in other words, you take the motion of these floats that you have coordinates for in a two-dimensional space of some shape, and you lift them to some space-time diagram. And the reason I plot time vertically in my braid diagram is that's the convention when you do plots, right? So t is usually going up in those plots, and you get a space-time diagram or world line of these trajectories, and then that makes almost a braid. Of course, there's a reason why it doesn't make a braid, and the reason it doesn't really make a braid is because it's not closed, meaning that the points that you start with are not necessarily the points that you end with as a set. In fact, it would be very surprising if they were. Only if you're sampling periodic orbits of a system do you get a closed braid out of this. So in general, you have to live with the fact that this isn't quite a braid. It's an object which is a little bit trickier to define than a braid. I'm not going to get into the definition of this. I will eventually just discuss the case where these things become longer and longer, in which case the fact that they don't close is not actually very important. Okay. So that is one convenient application of the braid group, is to transform data trajectories in 2 dimensions into a symbolic description in terms of generators. And the way you do this is fairly simple. You just keep track of the position of particles of your floats, say, and you pick a special line called a projection line. And what you say is whenever one particle moves above another one along the projection line, you say that this is like a sigma 1 generator. A sigma 1 generator has just occurred, and now you add it to the braid. And if the particle were to wander back across this projection line, that would make a sigma 1 inverse. Okay, so you just keep track of whether a particle is, whenever 2 particles cross along the projection line, you just look at which one is above and which one is below, and that determines which of the generators you record and whether it has a plus sign or a minus sign. Okay, so you can see in this case that they would actually immediately cancel, because of course they have not actually braided in any significant way. Okay, and this projection line is a little tricky because you can see the braid depends on the projection line, right? If I project along this direction, if I project the position of the particles now along a tilted line, I would get a different braid in general. So the relationship between these two braids, if they are actually closed orbits, these two braids are related via conjugation. Okay, it's easy to see that if you rotate this projection line, you're really just conjugating the braid, meaning that if the original braid is called alpha, then the rotated braid is beta alpha beta inverse for some other braid beta. So that's conjugation in the braid group. Okay. If the braid is not closed, then these things are not related exactly by conjugation. But again, if these braids are very, very long, then by changing the projection line, you actually make only a small error in the quantities that I'm interested in computing. Okay. By the way, of course, feel free to interrupt me if you have any questions. Right. Okay, so that's the connection between braids and the sort of data analysis that I have in mind when applying braids. And often, by the way, we are interested in having tens of thousands of these trajectories because we might sample, for instance, these trajectories from some dynamical system or something like a turbulent flow, for instance. So we might be interested in understanding the dynamics of a turbulent flow, and we do so by putting 10,000 particles. If you put 10,000 particles, you're going to get millions of crossings. So you're going to get enormous braids, and you need software that's kind of optimized for dealing with large amounts of braid. And I co-wrote a piece of software called Braid Lab, which we use for this, which is a MATLAB package that you give it the trajectories of many, many orbits, and it immediately turns them into braid. Of course, all of this has applications in magnetic fields as well. So in solar tubes, of course, you can consider them as braids, and you can do the same thing here to track the complexity of an entanglement of magnetic field lines, as many people in this room, like Mitch and like Gunnar, have done. Okay.
Jean-Luc?
Yes.
What happens if these generators at a certain level of time collapse for some reason? They are highly packed and entangled in a very specific time frame or local space.
Yeah, so you're saying that there's quite a few of them that are happening at the same time?
Yes.
Yeah, so in fact, that's an interesting question because when I initially wrote this software around 2010, I used a technique where I would try to capture all the crossings at once, and that's very tedious. But a student I worked with at the time, Michael Alshaus, realized that it was actually much better to always consider two pairs of strands, compute the crossings between these two pairs, and only after reconstruct the whole braid. That turns out to be much more efficient because then you don't have to worry about who's happening first, right? In fact, Renzo, you'll realize that whenever there's an ambiguity about which crossing is happening first, those actually correspond to commuting cases. So it's actually not that important to resolve that very carefully.
Thanks.
Yeah, so Braid Lab is actually, because we consider pairs of strands, it's actually parallelizable. So we can run the code in parallel and it can handle a large number of trajectories. It just has to remember what time everybody crossed and later on sorts the list of crossings, basically.
Okay.
Yeah. So it's extremely efficient, even when there's a lot of close crossings. I mean, of course, if your data is under-resolved for some reason, then that's a different issue. But assuming kind of perfect data, it has no trouble resolving a very complex braid. Okay. So what quantities would we want to extract from this? So one interesting quantity for us is the growth of a braid. And I'll just give a rough idea of what the growth is. Right. So the growth, we call it the growth of a braid. It's also going to be called the topological entropy in a second. But the idea is simply that if I have a braid, like this is the famous pigtail braid, right? Sigma 1, sigma 2 inverse. If I take a fictitious material loop, and I think of the braid as a rigid structure of metal, and then I force the loop to slide up, and the loop can stretch, then the loop will sort of, undergo kind of a pulling, and I can't do justice to the picture here, but it'll get folded in a way that you can imagine. And then if you repeat this braid over and over and you keep sliding your loop up, the loop will grow exponentially. Okay? So the growth of a braid is essentially the rate at which this grows. Or actually the topological entropy is the rate at which this grows. So growth or entropy is the rate of growth. Of course, the rate of growth of what? I mean, I'm thinking of the length of the loop, but you could also think of the number of crossings of the loop with some particular reference line. Almost anything will work because we are looking at the rate, and when you look at the rate instead of the growth itself, meaning you take the logarithm, right? You take the log of the length and you divide by the number, by time or something. That quantity is very weakly dependent on the metric. It doesn't depend at all on how you choose to measure the length of your loop. So this is actually sort of a universal characteristic of the braid, right? It doesn't matter how you try to measure the growth of your loops, you'll get some unique number, which is the topological entropy of the braid. So for the famous, sigma 1, sigma 2 inverse braid, the simplest Pseudo-Anosov braid, then the growth is golden ratio squared, right? It's 1 plus root 5 over 2 squared. And then I would say that the entropy is the logarithm of that, if you will. Okay, that's just a matter of definition. I'm not proving this, right, but this is an elementary calculation. Okay. So one big question that we struggle with, when we started looking at this a long time ago, is how do you compute this growth of a braid when you have a huge number of strands, right? When your braid has 10,000 strands and so millions of crossings, what is an efficient way of computing this growth? And the reason we want to know this growth is because growth, entropy bigger than 0 or growth bigger than 1 is a strong indicator of the presence of some kind of mixing process or chaos in the system. And for us, that's a good characterizer of the mixing characteristics of a fluid, right? Is understanding how quickly these loops grow. For instance, if you have a chemical reaction in a fluid, the rate of chemical reaction is exactly proportional to the material area between fluid parcels. Because the more interface you create, the faster the chemical reaction. And so we want to understand this growth in general. That's one of the things we're after. Okay. So the question is how to compute it. And there are by now very efficient ways of doing this. There's a very useful mathematical object called Dynamical coordinates, which I also sometimes call loop coordinates. And these are a set of coordinates that you can put on loops on the surface. I'm not defining loops very carefully here, but I essentially mean a simple closed curve. It could be a multi-curve actually, but think of a simple closed curve. Simple meaning it does not intersect itself. And Dynamical coordinates are a very efficient way of putting coordinates on equivalence classes of loops. They essentially look at intersections of loops with a triangulation, but it's even more clever than that because it's a one-to-one relationship between a vector and these intersection numbers. And then you can define an action of the braid group on Dynamical coordinates. It's a piecewise linear action, and by iterating this action, you can rapidly compute the growth of a loop. So it's piecewise linear, so it's not quite linear algebra that you're doing, right? Because there's a bunch of max and min functions. So you can't determine the growth by just looking at one iterate like you could in linear algebra. But you can still do pretty well. And again, this is the method that Braid Lab uses, the MATLAB code. And in a fraction of a second, it can do 1 million strands, right? So it's extremely easy as long as things are not a little bit pathological. It's extremely rapid. So that's one method. But I want to discuss today how you can use the Burau representation of a braid to do the same thing, and then how the Burau representation actually allows you to do some other interesting things that are rather novel. So I'll describe research, which is not mine, but it's a research out of Caltech a couple of years ago that I think you'll find interesting. Okay. So I'm going to erase, but is there a question before I continue? Okay. So now I'll describe very quickly the idea behind the Burau representation of braid groups. So of course, a representation of a group is some mapping from the group itself to some other object, usually matrices, but not necessarily matrices. For instance, if you consider the fundamental group of the disk, so you consider pi1 of a disk with 3 punctures, for instance. So what does that look like? Well, pi1 of D3 is the space generated by these loops. So this is a base point for my fundamental group, and there are 3 punctures because it's the disk with 3 punctures. D3 means the disk with 3 punctures, and these loops now are usually oriented. Okay, and so Artin realized that you could put an action of the braid group on pi1 by merely looking at what the braid group does if it drags along these loops. So for instance, if I do a sigma1 operation braid generator, that corresponds to clockwise rotating the first 2 punctures. So if you draw what the loop will look like, you will get something like this. So again, I'm taking these first 2 punctures and I'm clockwise rotating them. So I'm dragging along the first loop to now be in the second position. And the second loop has now moved to the first position. So let me write some arrows, and let me name these generators here, E1, E2, E3. So that means that this is the image of E1, this is the image of E3, and this is the image of E2. Okay? And so you can write this in the following way. You can write that E1 prime. So let's see. I would like to write the new generators, the image of the generators in terms of the original ones. And so E3 did not change. Nothing happened to the third generator. The second one was moved to the first position. So E2 prime is just E1 in terms of the original generators. The only tricky one is E2, or E1, sorry. And you can see that if I pinch here and I pull this over, what I'm really getting from this loop is I'm going to do an E1, then an E2, and then I have to do an E1 inverse to represent this loop in terms of the original generators. So this is E1, E2, E1 inverse. It's a very standard construction. Okay. So this is called the Artin action of the braid group on the fundamental group of the punctured disk. Okay. And you can do the same thing, of course, for sigma 2, right? So this is the action of sigma 1, the first generator, but you can do the action of sigma 2. And you can also see automatically what's going to happen to sigma 1 inverse and sigma 2 inverse. And it's not hard to convince yourself that this is a group homomorphism, right? That you're respecting all of the relations in the group. Okay. So such actions on free groups are extremely useful because they allow you to prove a bunch of things, because the braid group itself is not a free group because it has these relations. But if you're acting on a free group, you can use this action to prove that things are equal sometimes, because equality is extremely easy to prove in a free group. Whereas in a non-free group, there's all these relations you need to take into account to prove whether 2 things are equal or not. So this construction is extremely useful by conjugation. However, and you could use this to compute growth, the quantity I mentioned earlier. So how would you compute growth like this? Well, what you would do is you would take a braid, for instance, our famous sigma 1, sigma 2 inverse, and you would, transform the elements of the generators of the fundamental group, or any initial element of the fundamental group, first according to sigma 1, say, if you read these braids left to right. So that means that you would take this image, but then you would apply sigma 2 inverse to every single element of the image, because it's a group homomorphism, and then apply the transformation rule again. So you would keep applying this rule of how the braid group acts on the generators over and over again. And then the number of symbols, the growth rate in the number of symbols, once you take into account cancellations of adjacent words, adjacent letters, the rate of growth of the length of this word would exactly be the rate of growth of the curve here. So if you could measure how many symbols are appearing as you keep iterating this action, that would give you the growth of the braid. Okay. So in principle, this is very simple, and you can implement this in 3 lines in Mathematica, for instance. But there's a small problem with this. The small problem is that the number of symbols grows exponentially. And so after like 5 iterations of this, you run out of memory even on a modern computer. Maybe not 5, but of the order of 5 or 10 iterations. And the reason is that free groups are terrible to represent on a computer, right? It's just a bunch of letters. There's no cancellations. You have to maintain the order of all the letters. And so the only way to represent a word in memory is to list all the letters sequentially. So in order to measure the growth, you have to keep track of this exponentially growing number of symbols, and then you have to try to fit a growth rate to this number of symbols. It's not easy. It's not a natural way of doing this at all. Okay? And the reason it's not easy, or the reason why it's a bad idea, is it's not linear algebra. At the end of the day, we would want everything to be kind of like linear algebra, where we know how to manipulate matrices and things like that. Okay? So in principle, this representation is a nice way of computing growth, but in practice, it's just way too awkward, and we don't want to do it this way. For large braids, this would be a non-starter. You would not be able to do this. Okay. Is this fairly clear, what I'm not proposing here?
Is it related to Lyapunov exponent?
Renzo, it is a little bit related. It's the kind of topological equivalent of Lyapunov exponent. In fact, the topological entropy is an upper bound on the Lyapunov exponent. Yeah. So you cannot compute a Lyapunov exponent here because you don't have enough information, right? Like for the Lyapunov exponent, you actually need to tell me what the little fluid parcel is doing all the time. Whereas here, I'm only telling you some representative parcels, and I'm deducing some upper bound on the whole fluid based on these few parcels. But it's not a bad proxy for the Lyapunov exponent.
Right, but it was clear from the beginning that it was going to grow exponentially anyway.
Exactly. But that's important because it's an upper bound on the Lyapunov exponent. So strictly speaking, mathematically, it could be, there are systems with positive entropy, but 0 Lyapunov exponents. That can happen when you have chaos occurring on a set of measures 0, right? But in practice, for practical applications, this is actually a very rare case. So you still get a kind of good estimate of the chaotic behavior of a system by using topological entropy. The gap between the entropy and the exponents is a very interesting quantity, by the way, but I won't get into that. Okay, so as you can tell, I love doing linear algebra in the sense that, if you can reduce a problem to linear algebra, that's kind of what all of our software packages are designed for linear algebra. It's the greatest tool in the world, right? So what's a way to turn this into linear algebra? Okay. Well, there's a process called abelianization, a beautiful word. Abelianization is simply the idea that I'm going to assume that everything commutes, that everything is abelian. It's formally, or more rigorously, it means passing from the fundamental group of this surface to the homology group of this surface. The homology group is a commutative version of the fundamental group. So what that means is I can take E1, E2, E1 inverse, and I can think of it additively, because as soon as you're commutative, it's typically it's typical to just assume that you write everything in terms of addition. So I would write this as E1 plus E2 minus E1. Okay. And then you can see that the E1s cancel. And that's bad because now I have that E1 prime is E2 and E2 prime is E1. That's just a permutation. So the abelianization of this action just gives me the symmetric group, just gives me the fact that the braid group actually contains a symmetric group, and I've obtained a linear representation of the braid group, but that linear representation is just the symmetric group on n symbols. It's just reflecting the fact that I can interchange punctures, but it's losing the interesting thing about the braid group, right? Which is that there's a clockwise and an anti-clockwise interchange. So there's never going to be any entropy here, because if you compute the eigenvalues of these matrices, they're always going to be on the unit circle. You'll never get growth. You'll never get anything interesting. So canceling these generators, or sorry, abelionizing at this level doesn't really give you anything. By the way, the reason why abelionizing is the right thing to do is that abelionizing can only lower the entropy, and so you can still get a bound. In other words, I can only get a little bit of cancellation by abelionizing, but I still get an upper bound on the quantity I was trying to compute, or a lower bound, sorry, on the quantity I was trying to compute. Okay, right. So the question is there something you can do that isn't between? At one end, you've got the fully non-abelian fundamental group action on pi1 on the fundamental, right? And at the other end, you've got the symmetric group, which is the homological aspect of the punctured disk. Is there something kind of that splits the difference and allows me to have my cake and eat it too, at least to a certain degree? Okay. And the answer, of course, is yes, and that yes is going to be the Burau representation. So let me give a quick explanation of how this is going to work. So I keep my punctured disk, but now I'm going to make what's called a covering space of the punctured disk. So I will add some little cuts. These dashed lines are little cuts between the punctures and the boundary. What these little cuts mean is that now, if a loop crosses a cut, it's no longer on the same copy of the disk. So a covering space is the idea that you make several copies of your domain. We're not going to specify yet how many copies, but I think of these as little staircases. So think of the dashed line as a staircase. If I go this way, whenever I hit a dashed line, I go up the stairs and I'm now on the second floor. Or sorry, you guys are in Europe, so I'm now on the first floor, right? And by the way, these share a first floor. So if I cross these dashed lines, I'm always going to be on the same first floor. If I cross the other way, I go down the stairs, and now I'm back on the floor 0. Okay? So that means that these are no longer loops, in fact. They are arcs. Because I start here for E1, for instance, I go up the stairs, and I go back to the base point, but the base point is now on the first floor, right? So this is an arc connecting the base point to its image on the first floor of the building. So this is called a covering space, and you can represent it in terms of what's called a skeleton or a one skeleton. So let me show you what I mean. So this is a schematic representation. So think of this as the base point, and think of this other point as the image of the base point on the first floor. So I'm going to write this as Tx0. T here is a kind of translation. It's the operator that gets me to the next floor. Okay. So then E1, my loop here, is actually connecting x0 to Tx0. So I'm going to write E1 like this, and this is going to be E3, and this is going to be E2. Okay. So now, make a little bit of room. What about the next floor? If I go along E1 again, I get to a new copy. If I start from the first floor and I follow E1 again, I'm going to get to T squared x0. And I'm going to call this TE1, TE3. So in other words, you've got E1, you've got the translated version of E1, you've got E2, you've got TE2, you've got x0, Tx0, T squared x0, and so on. You can also go back down, right? So that just looks like the same picture, but going all the way down. And this picture could, in principle, go up to infinity. Each of these is a copy of my disk. Again, this is a schematic representation, right? Only it's just a way of looking at all what the arcs look like in this covering space. Okay, right. So why do I draw this picture? Because I'm going to look at the image now. Remember earlier we had that the image of the action the image of E1 was E1, E2, E1 inverse on the disk. The question is, what does that lift to in the covering space? Well, it's actually easier than you might think because everything still has to be continuous. But the construction of the covering space still maps arcs to arcs. So if I go E1, then I do an E2, well, it's a positive E2, right? So it can't be that I go E2 inverse. I have to keep going up. That's the only way to maintain continuity and have this be. So this E2 should actually be TE2 in the lifted space. And then the E1 inverse corresponds to coming back down like this. So in fact, in the covering space, the action should be the image of E1 under my braid sigma 1 should be E1 TE2, right? So E1 TE2 and then TE1 inverse. Okay. So let me just, so this is the image of sigma 1, which is the interchange of 1 and 2, which we saw had image E1, E2, E1 inverse. The question is, if I lift that object E1, E2, E1 inverse to this covering space, then it must be that it's E1, TE2, and TE1 inverse. Okay. And you can do this, of course, for all the generators, and you can shift this to all the copies. The copies are called decks. The T's are called deck transformations in this covering space picture. Okay. Right. Any questions before I do a little bit of erasure? Okay.
Continue.
Right. So I'm not going to need this anymore because now I'm going to immediately abelianize again. Because I have now a different action of the braid group on some space. The space is no longer the fundamental group, it's the covering space of the fundamental group, right? But I still have an action and I have the image of my generators under this action. And so I can write it additively. So let me write abel for abelianize. So if I abelianize this, what does it look like? Well, it means that E1 prime is E1 plus this generator is called TE2. And then TE1 inverse just becomes minus TE1. Okay. So now T is this kind of operator, but I can actually treat T like a number if I want to, because all I need is some counter to keep track of which deck I'm on. So I can take powers of a number to keep track of that. So let me just treat T like a variable. And so I can group terms together and get 1 minus T E1 plus T E2. Okay. So this is a very sketchy derivation of what is called the Burau representation, in the sense that now I actually have a linear representation of my braid group again, acting on these generators, this vector space E1. So it's a linear representation. But notice the coefficients now are 1 minus T and T. It does not give me the symmetric group unless I set T equal to 1. Right? If I set T equal to 1, then this is 0 and I'm back to where I was before. But if I leave T as a variable, the way it is now, I have a bona fide representation of the braid group, which is no longer a trivial thing like the symmetric group. Okay? And this representation is called the Burau representation. So the Burau representation is taking the action of the braid group on the fundamental group of a surface, but then lifting that action to a covering space of the fundamental group, and then abelianizing this. And what I get is the result of this is a matrix representation of the braid group. So let me discuss that representation. So this is called the Burau representation. B-U-R-A-U. It dates back to the I want to say 1920s or 30s. I don't remember the date of Burau's paper exactly, but it's an old representation. And let's see. Here is the representation of the element sigma 1. So this is the image of E1. So now you realize that it can, by the way, the square brackets are going to mean the matrix representation in the Burau representation of this group element. So 1 minus t, and then t, and then 0, and then 1, 0, 0, and then 0, 0, 1. So this is because the image of E2 is E1, and this is because the image of E3 is E3, which I didn't write there because they're the easy ones, right? So the 1 minus t comes from here, and the t comes from here, and the 0 is because there's no E3. So this is the matrix representing sigma 1, and so on. You can also write down now the matrix representing sigma 2, and you would always have this block structure where for the sigma 1, there's a non-trivial 2 by 2 block involving 1 and 2. For sigma 2, there would be a non-trivial 2 by 2 block involving 2 and 3. Okay, so there's the Burau representation as a block structure, basically because of the commutativity of non-adjacent strings, right? Okay. So this is the quote-unquote Burau representation, but there's a way to reduce it a little bit into what's called the reduced Burau by observing that the loop, if I take this loop, if I take E1 plus TE2 plus dot 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 Tn En, or sorry, Tn minus 1 En, this loop is invariant under the Burau representation, meaning if I act with any matrix on this vector, then it is unchanged. It's an eigenvector for all the matrices. By the way, I'm now generalizing to n punctures, but you can kind of see that, you know, if I just add ones here, I would get the representation for n punctures, right? It's not hard to generalize the Burau representation to n punctures. This loop, it's not surprising that it's invariant because it corresponds to the loop around all the punctures. Okay, if I make a loop around all the punctures, then clearly moving the punctures around doesn't change that loop. So there is a standard construction now. These are n by n matrices that we have right now. So if I have n strands, I would have n by n matrices. But I can make a modified or reduced Burau where I change basis. So I use this as one of the vectors of a new basis. And I also define a set of new vectors. U1 is E1 minus E2. U2 is E2 minus E3, dot, dot, dot. So there's n minus 1 of these. And then there's one more vector here. And so if I change basis to use the u's instead of the e's, I get a representation that blocks up because it has a unit eigenvector as part of the basis. And therefore, you get a matrix representation that has dimension n minus 1 by n minus 1. And it looks like this. It's called reduced Burau. And reduced Burau, well, the defining feature is that each adjacent set of strings carries a 3 by 3 block that looks like this. Is this a minus 1? No, that's right. So for each set of adjacent strings, I have a 3 by 3 block, and the minus t block is always in the, for sigma k, is always in the k position, the kk position. Sorry, I'm going a bit fast here, but what I mean is that this is possibly, if you do go on Wikipedia to find the Burau representation, you will get these types of matrices and not these types of matrices. And the reason is because the reduced Burau is more standard to write down as a representation for the braid group. Essentially, you can think of the reduced Burau as a representation on free homology instead of on homology. It doesn't, it removes the base point from the definition. Okay. Right. So it's not terribly important, but that's, I mean, I'm saying that the details here are not what I'm trying to get through, but the point is that you can reduce these to smaller matrices. And in the reduced Burau, the matrices have dimension n-1 times n-1. Okay, and that is the standard version of Burau that you typically see. Okay. Any questions?
Please continue.
Yeah.
No, please continue.
Okay.
No questions.
So, what is the role of the parameter t? Right. So I've been a little cavalier here. I'm treating t as a number. So t, in some sense, measures the degree of my covering space, because remember that as I take powers of t, I'm thinking of a new copy of the disk. So t in general could be a root of unity. So you could have something like t to the m is equal to 1. And then this would be an m-fold cover, right? So if I set m equal to 1, I have no covering space because 1 power of t and I'm back to where I am, so I'm not covering the space at all and I'm back to the symmetric group. If m is equal to 2, I have what's called a double cover, right? So if t is equal to -1, which is possibly the most important value that you can use, if t is equal to -1, then this is called a double cover. Okay, and you can pick other roots of unity to get higher and higher degree covers. And there's a theorem by, well, actually, let me return to that in a second. But the double cover often plays a special role. So it means there's only 2 copies of the disk. But in general, you can also leave t as a free parameter, or even think of it as an irrational, as a number which is not a root of unity, right? And in that case, the covering space is infinite and never kind of loops back on itself. Okay. So there's a theorem by Fried and Kolev that the eigenvalues of the Burau representation are a lower bound on the growth. This is essentially obvious, but there's some caveats which are important, that you really must use values of t which are on the unit circle. So if I call the growth here by the parameter lambda, then I can say that the growth is bounded from below by the spectral radius of the Burau representation. The spectral radius being the magnitude of the largest eigenvalue of a matrix. I left a bit of space here because I want to say that this is the supremum over all values of the Burau parameter on the unit circle. So I want to look at all possible values of t on the unit circle. T can be a complex number, and compute the spectral radius of the Burau representation of a given braid, right? And whatever the best value I find is a lower bound on topological entropy. Okay. Again, it's this part that's not so obvious, right? The fact that you can soup over this parameter requires a little bit of work to understand. But if you think of it about symbol counting, right? You're trying to put a bound on the number of symbols. In some sense, it's kind of obvious in this abelianizing process and with these complex numbers that you can't actually increase the number of symbols over the free group description. So to me, this is a little bit intuitively obvious, but to prove it requires some work. Kolev, for instance, used this free this kind of differential calculus on free groups, which was, it's a nice way of proving it. So Boylan and Harrington, or is it, no, Ban and Boylan, have a theorem that says that this is equality if, sorry, let me be careful. If this is equal, then it must be equal for t equals -1. So if we have equality in this lower bound, then t is equal to -1. Which is kind of a deep statement, actually, because it says that this can only be equal when you're considering the double cover of the space. And the reason why this is important is that when you have equality, you're reducing this Burau construction to the so-called orientation double cover, which is a very useful construction in this topological dynamics view, where you force a foliation to be orientable by taking a double cover. So the double cover really does play a special role. The t equals -1 plays a very special role in this whole construction. But it is not always the best value. In fact, we have examples where, you know, there are braids, such as, for instance, the braid sigma-1, sigma-2, sigma-3 inverse. There are plenty of examples of braids which that this bound is not an equality, but also that the best bound is not for t equals to -1. Okay, so that's a good example. You can see this. You know, you can try it for yourself using Braid Lab, for instance, that you can compute exactly the growth for this braid, and then you can try to find the optimal t for this, and you get a gap of about 15%, right? Like between the best possible bound and the actual value. So in this case, the Burau representation actually works pretty well. But there are instances where the Burau representation is arbitrarily bad at this. Okay. Let me just say another word about, there's another representation called the Lorentz-Kramer representation, which is a faithful representation of the braid group, but also has this homological construction. It's a more complicated homological construction, but it still gives you a lower bound on the topological entropy in the same way that the Burau representation does. And it is kind of an open question how much better Lorentz-Kramer is at characterizing the entropy. I've done a little bit of work in that direction. I have a student, John Lynch, who a few years ago derived a family of braids for which the Lorentz-Kramer bound was arbitrarily better than the Burau bound, right? So in other words, it is possible to have braids which are somehow the Lorentz-Kramer construction on the homological construction captures the entropy better than the Burau construction. But I don't think this has been characterized yet. Nobody really knows what it is about a braid that will give it a better Burau bound versus a better Lorentz-Kramer bound. So that's for the experts in the room who know about these different representations. Let me also say that the issue of faithfulness of the Burau representation I don't think is very important here, in the sense that I used to think that the fact that the Burau representation was not a faithful representation of the braid group, I used to think that that would matter, but in fact, in practice, I don't think these homotopic and homological questions are really deeply connected to the faithfulness of the representation. Okay. I think I might just skip over the last part and just give you a very, very quick flavor of what I have in mind, because I'm really running out of time. That's the problem with board talks, right? They always take longer than you think. So let me just mention quickly the work of Young, Cohen, Steiner, and Debrun. So Young, Cohen, Steiner, and Debrun are at Caltech, and they published a paper in 2020 where they used the Burau representation to identify what's called coherent structures in a flow. So there's a paper by me and Michael Alshaus where we this is 2012, I think, where we try to extract information out of a braid, in particular having to do with isotopy classes. So braids are often what's called reducible, meaning that there is a distinguished curve that you can draw in the braid such that that curve does not grow if you slide the curve along the braid, or it grows slowly, not exponentially. Okay, and the reason why we care about those is that in a, say, ocean float situation, if there's a group of floats trapped in a vortex, then they don't interact with the outside world in a significant way. Even if this vortex is moving around, the floats in the vortex, in some sense, don't carry their own growth. They don't cause any entropy. And it's often useful to identify such clusters. In the literature, this is called Lagrangian coherent structures, or LCS. This is a word that was coined by George Haller in the early 2000s or late 90s, I think. And in our paper, we found these curves by a kind of search algorithm cleverly devised by Michael to kind of look at pairs of strands and kind of to decide which caused growth of curves and which didn't. And it works, but it's a little bit laborious. What Young, Cohen-Steiner, and Debrun did is to use the Burau representation to do this. The idea being that slow-growing curves correspond to special eigenvectors of the Burau representation of a braid, which have sort of piecewise constant entries. So by using essentially matrix decomposition techniques on the Burau representation, you can identify such clusters in data. And so this is very nice because, again, because it uses only linear algebra, it only uses the Burau representation, it scales extremely well, right? You can easily tackle 1,000 or 10,000 particles because all you're doing is manipulating large matrices, and that's what computers are really good at. So I'm sorry that I ran out of time to describe this algorithm. I was going to spend a little bit of time describing this, but it's a nice paper if you want to read it. It's in the journal Chaos. Both of these are in Chaos, actually. So feel free to look them up. Okay, I think I'll stop there. Thank you.